Hey, grade 8, welcome to the continuation of your topic around water systems. Today we're talking about freshwater and specifically different forms that freshwater can take, how freshwater kind of feeds into oceans and stuff. So that's today's lesson. I'll be honest that this lesson is kind of more than anything a vocabulary lesson. So it's really important that you understand the terms and just kind of learn some of the points. But it gets pretty specific at times. Just make sure that you understand the big ideas behind this. So let's get into it. First of all, freshwater can exist in kind of like two different places or forms, either as surface water, which means it's above the surface of Earth, and then also as groundwater, so it's under the ground. Pretty self-explanatory, but it's important that we kind of understand that distinction. It's important, and we're going to really focus on that distinction in this lesson. So we're going to start by talking about different types of surface water and how that looks. So let's begin with lakes and ponds. Lakes and ponds are really similar, right? We all know kind of what a lake or a pond is, and the big difference between the two is the depth. So at maximum depth for a pond, the sun cannot reach, can reach the bottom of the pond. So we take a look at the bottom of the pond, sunlight is making it to the very bottom. Well, that is not true for a lake. A lake is too deep or has too much sediment and stuff for sunlight to make it to the very bottom. And of course, that has a big effect on, for example, what kind of aquatic plants can grow in the lake at the bottom. So the amount of sediment in a lake or pond affects how deep the sunlight can actually reach. The amount of matter suspended in the water is called clarity. So we talk about clarity of water, we're talking about how clear the water is, which I think makes sense. A high sediment load, so when we have a lot of sediment in that water, we have low clarity. And if we have less sediment in the water, it's very clear, then it is very clear water, so it has high clarity. So we've all seen those pristine images of lakes where you can see the very bottom of that lake, but I guess, would make it a pond, but you know what I mean. And that would be then a very high clarity water. And we've also seen low clarity water, so when you have really muddy streams and stuff, then that would be lower clarity. And of course, the clarity affects how much sunlight can make it to the bottom. Let's talk about wetlands. Wetlands are super important, and you watched a Bill Nye video yesterday about wetlands. You know it's important for filtering water and so on. And also there are a lot of organisms and species that rely on wetlands as their habitat. And it's low-lying areas of land where water accumulates and stays for most of the time. So wetlands are fully saturated, which means that they are full of water all or most of the time. And wetlands provide habitats for many plants and animals, and of course play a role in filtering and cleaning water as well. They are very important, but unfortunately wetlands are often being destroyed, as you also learned about in that Bill Nye video. Let's now talk about rivers and streams. Rivers and streams are both fast-flowing waterways. Rivers differ from streams only in the volume of water they hold. So streams will have, of course, less water, while rivers will have more water flowing through it. All flowing waters, rivers and streams, differ from each other in speed, in temperature of the water, in clarity, right? The more fast moving and so on it is, and turbidity, then we're going to have less clarity, and the nature of their bottoms and banks. So all rivers and streams are different. So when taking a look at this picture, which one do you think is the stream? And that's right, it would be the middle one. You can see that there's quite a bit less volume here than there would be in this larger river right here. And then this would be a lake. Okay, looking at it, it looks very deep, and I'm assuming that sunlight cannot reach the bottom. The speed, volume, and timing of the flow determine how the river shapes the surrounding landscape. So as you know, rivers over time can erode and change landscapes in order to make valleys and canyons and everything else. When you look at the Grand Canyon, that's just a river that has eroded over a very long period of time, that area, resulting in what you're seeing. So rainfall, melting, snow, and the amount of groundwater influence the volume of the flow through a river or stream. And monitoring streams help scientists, or rather stream flow, I should say, help scientists to analyze water quality, to prevent or warn people about floods, predict drought, and to design irrigation and drainage projects. So all the time, different rivers and streams have their stream flow measured. So figuring out how much water is passing through that river or stream, which provides very important information. This is done, for example, when it comes to the South Saskatchewan River, so that we know if things are going to flood or get a little bit scary and what the water level will look like. Also very important when it comes to irrigation, right? Knowing how much water is available for irrigation. All right, above ground, also rivers and streams. A river can shape the surrounding landscape. We already talked a little bit about this, but factors that influence how much it can shape the landscape would be things like speed of the water. Faster water is, of course, going to have faster erosion and faster effects than slower water. The timing of flow, is it just for a short period of time? Is it all year? When does it happen? How is the soil during that time, or the surrounding materials? Is it still very hard, or is it saturated with water? That sort of thing. The volume of water flowing. More water means, of course, there's going to be more erosion and eating away at the landscape. So these are just a few things to think about in terms of how fast the landscape might change from rivers or streams. Now, I think this is all pretty common sense, that of course these things are going to affect how much things change. And again, I have the same statement here. The volume of water is influenced by rainfall, snow melt, and groundwater. So here's a quick kind of diagram showing the idea of stream flow and how to calculate stream flow. So by figuring out the cross-sectional area of a river, and then from there figuring out the velocity of that river, we can figure out stream flow. This is just one little section, right? Because it could change in different areas, so it's best in terms of the flow, the velocity. So it's best to actually just take a small section at a time, figure out how much area this would be, and then from there multiply it by the velocity of like how far it travels in meters each second. And then from there we can figure out stream flow. You don't have to do any of those calculations, but it's just kind of interesting. And how could you figure out the velocity? Well, just put something in there, just have it floating and see how far it goes in that period of time, and that's your velocity. So that's the basic idea of calculating stream flow. All right, watersheds. Watersheds are massive areas that all kind of come down into the same place and then end up draining into the same location. So watershed is an area of land that drains into a body of water, such as a river, a pond, a wetland, a lake, or an ocean. So we can talk about this in a smaller scale when it comes to like a lake or a river or a pond, or we can talk about this on a very large scale when it comes to, for example, going into an ocean. So talking about it on a large scale in Canada and states, North America, period, the Continental Divide is a range of mountains that divides the American continent into two main drainage areas. One side drains into the Hudson Bay or Gulf of Mexico, and the other drains into the Pacific Ocean. So of course we're talking here about the Rocky Mountains. If we take a look, you can actually see that Continental Divide. That's the red dotted line, and then you can see that water from the west of those mountains goes west into the Pacific Ocean, while from the east we go into the Hudson Bay, going into the ocean, or into the Gulf of Mexico, which both, of course, are feeding into the Atlantic Ocean. So just kind of interesting to see how that works out. And just neat, right, that we have this divide, and then the watershed, as a result, drains water into the different areas or different oceans. Here's another couple of diagrams. We're not going to go too deep into this, but just showing in Alberta different kind of watershed areas that go into rivers, right? So we have this blue watershed going into the Peace Slave River Basin. We have, of course, the South Saskatchewan River Basin that we're a part of right here. So goes into that river, and that's the watershed. So different watershed areas. So basically you kind of pick your body of water, right? And then from there you figure out the watershed of what's feeding into that body of water. Talking more about watersheds, landforms determine the size of a watershed and the speed and the direction of the water flow. The upstream areas of a watershed are called headwaters, so kind of at the very top there, and the end point of the watershed is called the outflow. So headwaters at the top, head outflow at the bottom. Head being at the top. That's the trick. So above ground watersheds, again, the amount of runoff in a watershed is influenced by how saturated the soil is before the rain happens, the amount of rain that occurs, the time it takes for the rain to fall. Is it super fast, resulting in a flash flood, or is it a slow rain over many, many days? The slope of the land, how drastically sloped down it is, and the amount and type of vegetation. So these are all things that will influence the amount of runoff into or in a watershed area into that body of water. Of course, more vegetation is going to slow it down as well. In urban areas, we have more runoff because of the fact that we have pavement and asphalt, which is impermeable to water. So as a result, less of it absorbs. And rivers carry water downhill to a lake or an ocean. The headwaters higher in the mountains move very, very fast. And then as they go, they will get slower. As they move, they erode or take materials from their bottoms and banks, such as loose boulders and sediment. And then afterwards, they'll deposit. And when rivers slow down, the sediments get dropped down to the bottom, and this is called deposition. This was kind of a really interesting thing when it came to trying to find gold in rivers and streams, because they would look for the points where gold would actually settle down based on water flow and how that would work. Anyways, I feel like most of this is kind of common sense, right? It makes sense. The water flows downhill. Pavement and asphalt, the water doesn't soak into. Vegetation slows down the water. Higher up is called headwaters because your head is on top. Okay, and then as it goes down and down and down, it's going to get slower. Mainly because the slope is going to get less. And then as water flows down, it carries and erodes stuff away. And then as the water slows down more and more, it leaves that stuff behind. And that's the deposition. Stream flow, we've already talked about a bit, is the amount of water released by a watershed. It involves measuring the amount of water volume that flows to a certain point over a period of time velocity. So we can do this for a watershed as well, not just a river or a stream. But yes, trickier to measure, but still something that we can calculate. Or you can actually probably just figure that out too by how much water is being added to the river or the stream. Above ground, still on watersheds, stream flow information is very useful to us because it can help us analyze water quality, help warn people about floods before they happen, help predict drought conditions when the watershed is not feeding as much water, and help design irrigation drainage projects. This is exactly what we were looking at for streams and rivers as well, essentially. Same kind of things. It's important for us to measure stream flow for these reasons so we can basically plan, predict, be proactive. Monitoring of sediment that's left behind in a watershed is important so scientists can actually take a look and determine what type of pollution we have. They can assess the impact of pollutants on the aquatic environment, and then steps can be taken to reduce that pollution. So it's important to monitor the sediment that is in watersheds and to make sure that things are staying healthy for aquatic ecosystems that rely on that water. The loss of soil due to processes such as runoff is referred to erosion. Excuse me. You're seeing erosion here in these pictures, right? So you're seeing both kind of erosion as the water flows and then also some deposition in different points as well. Erosion, big problem. Carrying away good soil and nutrients. The way to stop erosion, though, it's really simple. You just have to plant vegetation. The more vegetation you have, it's going to slow down the water. It's also going to cause anchoring as roots kind of travel through the soil, and that helps to prevent further erosion. So, especially on river banks that are crumbling into the river, the more vegetation we have, then again, the root system and so on will prevent that erosion or minimize it from occurring. So vegetation is the key to preventing erosion, and the more we destroy vegetation, the more erosion takes place. Let's talk about below ground stuff. So groundwater systems use spaces called pores between the soil and rock particles, and these pores allow water to sink down and get deeper and deeper. If the pore spaces are connected and water can go through them, the rock and soil are called permeable, meaning stuff can get through. The opposite of permeable is impermeable, which means water cannot get through. So sandstone is a good example of a permeable rock, Well, something like clay has no pore spaces, does not allow water to go through, which is why clay is great to build containers out of to hold water. And so it's impermeable. Water can't go through it. A well or a hole may be dug to reach water below the water table and bring it to the surface for human use. So then we're going into an aquifer, right? Tapping into that. If the aquifer has pressure in it because it's like well below the earth and there's a clay layer over top, then water will actually, once it's drilled, go up that well without having to actually apply any pressure or pump it or whatever, which is kind of neat. A spring is when groundwater naturally comes out of the ground into the surface. So that's what we're seeing right here. We have a spring where the groundwater is able to get out because the water table is higher, okay, than the actual ground at this point. And so we get a spring as water flows out of the ground. So well and spring. Any addition of undesirable substances to groundwater by human activities is considered contamination or pollution. You're going to talk about this in grade 9 as well. But when we talk about pollution, we talk about two different types. We talk about point source, which means we can easily identify where it's coming from. It's normally coming from a small confined area, like let's say a smokestack or something, or a pipe that is releasing waste into water. And we can say, hey, there it is, there's the pollution. Well, if we have a non-point source, it's harder to find because it's a larger area. It's not something that's easy to identify. So for example, it might be runoff from a farmer's fields that's introducing more fertilizer or pesticide to aquatic ecosystems. And that's really hard for us to track. It's hard for us to point and say, there it is, because it's a huge, large area. Maybe it's going way upstream, like the pollution is happening way upstream and then it gets carried way further down the stream, down the watershed. It's tough for us to know. But we're talking about groundwater here, and that can soak into the ground over time and make it into that groundwater as well. So that's the difference between point source and non-point source. Point source, you can point to the thing and say, hey, there it is. Non-point source, you cannot point to the thing and say, there it is. Let's talk about aquifers. When water is able to move from pore space to pore space, it makes a water system called an aquifer. When all the pore spaces and permeable rock are full of water, they make a water table. So here you're actually seeing aquifers, which are just kind of like these big reservoirs of water, essentially. There could be, material and stuff in there as well. But yeah, so you have these big areas of water. And here we actually have a confined aquifer, which means that it's under pressure because there's a clay layer on top of it. So there's pressure from everything else pushing down on it. And just like a water balloon where you poke a hole, water will, because it's under pressure, come out of a well if you drill it into the confined aquifer, which is kind of neat. And here we have the water table and there's the lake, right? So you can see that the water table is here, but it's saturated soil, and then the lake is at the exact same level. And that's it. A lot of definitions and stuff in this unit, a lot of just things to take a look at and make sure you understand. At the end of the day, it's just really important that we understand that fresh water is in all of these different forms, how watersheds end up resulting in water feeding down into larger bodies of water that eventually make it into oceans and so on. And yeah, just a lot of different kind of points, but what it comes down to is you just understanding a little bit of how fresh water travels and flows throughout Alberta and Canada and the world. All right, have a good rest of your day.